Hi and welcome to our review for 7.5. Alright, let's get started with, of course, some definitions and properties, and then we'll do examples. Alright, so this whole section is about conditional probability, and that is the probability of an event occurring given that another event has already occurred. So hopefully that makes sense. Conditional, right? The probability of a certain event is conditional upon another probability, right? So looking at the second bullet point here, this is the conditional probability of B given A, right? So you use B first and then A. So it doesn't matter whether you use B first and then A or A and then B, right? So it does matter the order, but that's given by the probability of their intersection divided by the probability of A, assuming that the probability of A is not 0 because we don't want to divide by 0. And what's over here is what's called a multiplication rule, at least that's what the textbook calls it, multiplication rule. And then you'll see it here too and here, right? But it's just rearranging the equation a little bit to multiply by probability of A on both sides of the equation. You get that. And then, all right, of course, there's a conditional probability of A given B, which is, again, you take the probability of the intersection, but now you divide by the probability of B, assuming that that's not 0. And the way I remember it is just, it's always the probability of the intersection no matter what, of whatever shows up in the parentheses here or here. So always the probability of their intersection, and it's always divided by the probability of the one that shows up on the right of that bar, right? So in this case, it's the probability of A that shows up at the bottom, and in this case, it's the probability of B that shows up at the bottom. It's kind of a way of remembering it. Okay, and then the last bullet point there says two events A and B are independent if the probability of A given B is equal to the probability of A and the probability of B given A is equal to the probability of B, meaning that the outcome of one does not affect the outcome of the other. So it just means that just because the event A has occurred does not mean that affects the probability of the event B and vice versa, right? They do not affect each other. And so when that's the case, what you can do is you can go back and say, all right, so if this is true over here, if the conditional probability of A given B is equal to the probability of A, then in this equation up here, then we have that this right here is just going to be the probability of A, right? Because if the probability of A given B is equal to the probability of A, then you just get that the probability of the intersection is equal to the probability of B times the probability of A, which is what you get at the bottom. And then, of course, if you use this equation right here and you're assuming that the probability of B given A is equal to the probability of B, then you can go up here if you were to scratch that out, because the probability of B given A is equal to the probability of B, you still get the same thing, which is ultimately what's at the bottom here. So in essence, if you're asked whether two events are independent, all you have to do is take the probability of one times the probability of the other, and then check to see if that's equal to the probability of their intersection. If that's true, yes, independent. If it's not true, no, not independent. That's it. All right, now we look at some examples. We'll jump to this one over here. Let's erase some of this. All right. Okay, so we have a few questions. That's supposed to read E over here, obviously. Okay, so let's answer these questions. Given that we know, so they tell us that these two right here are independent events. So we are given this. We can assume this for all of these questions. We're told the probability of A is 0.45, the probability of B is 0.35. You want to find the probabilities below. Okay, so let's get started. So for part A, alright, so remember the probability of A intersects B, if A and B are independent events, we know that it's supposed to equal the probability of A times the probability of B. Alright, so we know what those are, so we end up with 0.45 times 0.35, and when we do that, this is equal to 0.1575, and then we can round to 2 decimal places, so this is approximately 0.16. Alright, so easy enough. This is the probability of A intersect B. So just as a reminder, whenever you have to round off answers, that's usually the last step that you should do. So for example, if in the next step we need to use the probability of A intersect B, I'm going to be using this value right here, the exact value, rather than the approximated value. Okay, let's do probability, so that's part B. Find the probability of A union B. Okay, well this just goes back to what we knew from earlier in this chapter, that the probability of a union is equal to the probability of one element plus the probability of, not elements, probability of one event, sorry about that. So probability of A plus the probability of another event B minus the probability of their intersection. Right, because remember that we do not want to assume that these events are mutually exclusive. All we know is that they're independent, so you gotta be careful. You don't want to assume that the probability of A or B is just equal to the probability of A plus the probability of B. You have to make sure that you subtract this quantity over here just because you don't know that they are mutually exclusive. Okay, so let's do it. So this is equal to, we would have 0.45 plus 0.35 minus, now the probability of their intersection is what we got in part A, 0.1575. Okay, and once I do that, what do I end up with? This is equal to 0.6425, or approximately 0.64. So I want 2 decimal places. Okay, so we have A intersect B, we have A union B. Next, part C. The probability of A given B, or really the conditional probability of A given B, is equal to, we use the formula, right? This is the probability, you take their intersection. Then you divide by the probability of B. Okay, probability of their intersection is 0.1575. Divide that by the probability of B, which is 0.35. And you end up with 0.45. But hopefully by now, if you remember what independent events are, you would see that it's unnecessary for me to have computed this. Why? Well, remember that the fact that I know that A and B are independent tells me that the probability of A given B is still equal to the probability of A. And the probability of B given A is still equal to the probability of B. Right, these two probabilities, right, they're like one event occurring does not affect another event occurring, which means that the probability of A given B here should just be equal to the probability of A in the first place. So I could have got this 0.45 without having to compute this part. I didn't have to because I was told that these events are independent. I went through and did it anyway as a way to check and to practice doing this, but when you're told that events are independent, immediately think back to this property over here. So I didn't need to do this part. Okay, and then, all right, so let's go to D. Now I want to do the probability of A complement union B complement. So a few ways you can do this, but the way that I do this is I remember the Morgan's laws. So I remember that A complement union B complement is the same thing as A intersect B and then complement. So meaning this, I want to find the probability of A intersects B complement, because I know that this set right here is equal to this set over here by the Morgan's laws. Okay, I'm trying to find the probability of the complement of a set, and then I remember, oh, that's 1 minus the probability of that set, right? So meaning the probability of A intersect B. So, and I know what the probability of A intersect B is, so I can say that this is equal to 1 minus what I got in part A, 0.1575, and then that gives me 0.8425, or approximately 0.84, since I need 2 decimal places, right? That's my answer for part C. Okay, so that's one way to do it. Obviously, you can find the probability. There are other ways to do it, but I'm just gonna leave it at that. This is how I would suggest you do it. All right, so the last one, I want to find the probability of A given B complement. So if we use the formula that we know, this is gonna be equal to the probability of A intersect B complement. And then I want to divide by the one on the right, so the probability of B complement. Okay, well, the probability of the complement of an event is 1 minus the probability of that event. So I got that part. But how do I find the probability of A intersect B complement? So remember, A intersect B complement is everything that's in A and not in B. So what I like to do for these kinds of problems, and in general, really, probabilities included, Venn diagrams can sometimes be super helpful. So I'm gonna draw one up here. And maybe that might be helpful to you too. Okay, so Venn diagram here. Alright, so this is the entire sample space. Let's say we have a set A here, and then B is right here. So inside here, I'm going to put the probability. So not the number of elements, but the probabilities. So remember, whenever I fill out these Venn diagrams, I always start from the inside out. So I always take care of the intersection first. So in here, in the intersection, and since I don't have much room, I'll put it out here. The probability is 0.1575. And then I remember the probability of A is 0.45. But I already have taken up 0.1575 in the middle, so what's left out here is 0.2925, right? Because that's 0.45 minus 0.1575. Now, what is A intersect B complement? That's everything that's in A and not in B. That's everything that's in this piece over here. So what is the probability of that? It's exactly this quantity that we've just calculated. So going back over here, the probability of A intersect B complement is just that 0.2925. In other words, what you needed to do is take the probability of A minus the probability of A intersect B, and that's how you find the probability of A intersect B complement. Okay, so finally this is equal to, you have 0.2925 at the top. 1 minus the probability of B is 1 minus 0.35. That's given up here. That's the probability of B. Alright, so then that's equal to 0.65. And then when you divide the two, you end up with 0.45, which of course is the probability of A. Right? So now we can see that that A and B complements also are independent events, same as A and B. So this is really all that you need in order to be able to do the quiz, at least the part that's on 7.5. There are ways to do problems in 7.5 using the tree diagrams, but I will save that for the next video.